Let's take a look at another example where we have to use the Supermesh technique. So in the circuit below, we want to find the values for our three mesh currents I1, I2, and I3, which as you can see have already been defined in the circuit for us. So a couple things to note before even considering our Supermesh technique and whether or not it's needed, we can say we have three meshes, so M equals 3, so we know that we're going to need three equations. Now, as we take a closer look at this circuit, we notice that we have this current source of 3 amps, which is shared between two of our meshes. So in this case, it's shared between mesh 1 and mesh 2. And so anytime we have a shared current source and we want to use the mesh current method, we need to incorporate a supermesh, excuse me. So shared current source means we're going to need a supermesh. And so a couple things to note about that, as we saw in the previous video, that doesn't change our mesh current definitions. We're still going to use these original three mesh currents. We're just defining a different path which needs to avoid this branch containing our shared current source. So let's make a note of that. So let's say we're going to use a path that avoids that shared current source. And then one last thing to point out as well is that because we're having to use this supermesh technique, it does not change the number of equations that we need. We are still going to need three equations. It's just that we're going to get them from different areas. So it turns out for this circuit, we actually have a couple different options in terms of how we define our supermesh. So I've got our circuit copied here. I've just excluded the values because we're not really concerned with the values at the moment. We're just going to determine which path we want to use. So again, the goal is we want to avoid this branch here. So if we look at option 1, we can go around the perimeter of the circuit. So we go through the voltage source and those two resistors on the far right. So that's our first option. The second option is that we can go through this voltage source, through these sort of internal resistors, and then through that resistor on the bottom right. And you'll notice in both of these paths, we have avoided going through that shared current source. And that means that both of these would be valid options for our supermesh. So let's make a note here that both are valid supermesh paths. Both are valid supermeshes. However, let's take a closer look. So if we look at option 1 over here on the left, we notice we're going to need three terms. We're going to have a term for our voltage source, a term for these two resistors on the side. So we're going to need three terms here. And with these two resistors over here on the side, these are perimeter resistors. So they're going to be a little bit simpler to deal with because they only have one mesh current associated with them. So for example, this top right resistor only has mesh current I3. So resistors only have one current. Now, if we focus our attention on option 2, we can see that we have our voltage source term. We now have three resistors that we have to consider. So in this case, we have four terms. And so I am saying four terms and three terms. And of course, I'm talking about for our supermesh equation. We'll see that explicitly here in a little bit. And in addition to having one extra term, we note that for these two internal resistors here and here, those two resistors have multiple mesh currents associated with them. So for example, if we look at this resistor here, we notice that it has mesh current I1 as well as mesh current I3. And so what that means in terms of our equation is that's going to complicate it a little bit. So let's go ahead and say some of these resistors, and in this case we know it's going to be two of the three, have two currents, two mesh currents associated with them. And again, that's just going to make our equation a little bit more complicated. So ultimately, it's just your opinion in terms of which path you want to choose, and oftentimes we'll have more than two options. But in this case, it certainly seems like option 1 is going to be our simpler choice. So that's what I'm going to show here in the notes. But of course, you could work through using option 2 and you should get the exact same answer. Okay, so let me copy our circuit from above, and let's go ahead and get started on analyzing this circuit and finding those mesh currents. And so let me also go ahead and draw in our supermesh for clarity. So we said we're going to use option 1, so this is our supermesh path. So let's go ahead and label that as our Supermesh, and notice I've not defined any new currents. We're still using those original 3 mesh currents. Okay, so let's start by doing our Supermesh equation. So Supermesh. So again, when we're applying this KVL, we can start at any point and go in either direction. To be consistent with the notes, I'm going to start in the bottom left corner and go clockwise around that loop. So if we do that, we go through the 6-volt source first. As I've done in several of the examples up to now, we get -6. I can go ahead and move that to the other side, and I can say that 6 is equal to. Next, we go through our 2 ohm resistor, which, as we said, only has the one current I3, so that's just going to be 2I3. And then we go through our 8 ohm resistor, which just has I2, so we have plus 8I2. Now, sort of thinking ahead, I know I'm going to want to use matrix method again because that's going to scale up nicely, so I want to get in a habit of using that. To make this easier to plug into our matrices without making any mistakes, I'm going to go ahead and include an I1 term. Now, of course, the coefficient of that is going to be 0 because it doesn't show up, but that's going to make it so that I'm less likely to make a mistake when I'm filling in those matrices. So I'm going to say 0I1 plus 8I2, and I'm going to go ahead and reorder these as well so they're all in the same order, I1, I2, I3 terms for all of my equations. And so there's our sort of simplified version of our Supermesh equation, and I'll call that equation 1. Okay, so our second equation, we know whenever we're doing Supermesh, we get one equation from the Supermesh, we get the second equation from looking inside the Supermesh. So I'm going to come down here and let's say we're going to get this equation from looking quote unquote inside our Supermesh, which I'll just abbreviate as SM. And so what that means is we want to look at this shared branch here. And remember, there are 2 ways that we can determine the relationship between, in this case, I1 and I2 and that current source. We can look directly at this branch and we can say we've got our 3 amps going in this direction, our I1 going in this direction, and our I2 going in the opposite direction. And so from that, we could say, for instance, we know our 3 amps is going to be I1 minus whatever I2 is pushing in the other direction. So I could come here and I could say our 3 is equal to I1 minus I2. Alternatively, if that doesn't make as much sense to you, we could also do a KCL at either of the 2 nodes associated with the branch. In this case, at that top node, we would see we have I3 coming in and going out, so we ignore it. However, that could be a little confusing, so it might be better to focus on this bottom node, in which case we see we have I3 coming in, I2 coming in, and I1 going out. And so we could write that down, rearrange it, and we would end up with the same equation that we see here. And so you could do that for yourself for practice. So again, I'm going to rearrange this equation so that it's a little easier to put into matrices without making any sort of silly mistakes. So I've noticed I have my I1 term minus I2 term, and then I'm going to put explicitly plus 0 times I3, and we know that's equal to 3. So I'm going to call that my equation 2. Okay, so we've done our Supermesh, we've looked at inside the Supermesh, but remember up here at the very start, we said that we needed 3 equations. So where is that third equation going to come from? So you might even want to pause the video for a bit and see if you can't figure out where that third equation is going to come from. So what we can notice is, of course, we can't write an equation for mesh 1 or mesh 2 because both of those involve this shared current source. And when we get to that current source, we don't know what the voltage across it is. So we can't do mesh 1 or mesh 2. However, our mesh 3 does not go through that current source, and therefore we can get new independent information by analyzing our mesh 3. So let's go ahead and write an equation for mesh 3. So coming down here, let's say mesh 3. All right. And so again, you can start at any point, go in either direction. Excuse me. To be consistent with the notes, I'm going to start in the bottom left and go clockwise. And so we see first we're going to be going through that 2 ohm resistor. Excuse me. And we see that the 2 ohm resistor, we have I3, or we could think of this a couple different ways. We have I3 going up, we have I1 in the opposite direction, so it's going to be I3 minus I1. Again, because we're in the mesh 3, we're writing an equation for mesh 3, I3 should always be positive, so we could just say 2 times I3 minus I1. Either way you want to think about that, we get 2 times I3 minus I1 for that first term. Coming back up here to the circuit, the next resistor is going to be this 2 ohm on the perimeter, and that's just going to be 2I3. So plus 2 times I3. And then finally we have this shared 4 ohm resistor where we have I3 in one direction and I2 in the opposite direction. So we're going to have I3 minus I2. So this is going to be 4 because we have a 4 ohm resistor, I3 minus I2, and we set that equal to 0. So here we don't have to sort of include any of those terms with a 0. We don't have to add that in because all of them are naturally there. So we just need to collect our terms. So we've got negative 2I1 minus 4I2 plus 8I3 equals 0, and we'll call that equation 3. Okay, so now what we can do is we can take these three equations and we can use our matrix method to solve, because we have three equations with three unknowns. So our unknowns are, of course, our mesh currents, I1, I2, and I3. So let's go ahead and show how we would do that. So we have I1, I2, I3, and we know that's going to be equal to the coefficient matrix. So the first row comes from the first equation, 0, 8, 2. Second equation gives us our second row, so 1, negative 1, 0. And then third equation gives us our third row of negative 2, negative 4, and 8. So we invert that matrix. We multiply it by our constant matrix of 6, 3, and 0. And we plug that into our calculator or into MATLAB. And again, if you have any issues about doing that, let me know and we can go over that in detail. But in this case, we get that that's approximately 3.474, 0.474, and 1.105. Now, because all of the values I plugged into my equations were volts, ohms, and amps, then that means these currents are also in amps. And so that is the answer to the initial question of what are the three mesh currents.